Thank you, Max. Thank you for having me here to give this talk. So this will be based on the recent paper I have with Alonso, who is a PhD student at Virginia Tech, and he will also be in the postdoc job market this cycle, Eric Sharp, and of course myself. And many of our results is based on this very profound work by Saakashvili and Krumnovafa about the superstring theory on the exceptional holonomy manifold. So we will use lots of results here. And since I'm giving a Blackboard talk, so I might be doing a bad job in like citing other references in some minor points. So I ask for your apologize. Okay, so basically the two things I've been interested in today is the modular spaces and the symmetries. So of course, modular spaces are very important in both, mathematics and physics. So you can think of this as the parameterization of some kind of property of your geometry or even some other kind of object, right? So let's say, of course, the very celebrated example is for Calabi-Yau, right? You can, of course, you have the modular space for Calabi-Yau, you have the complex structure moduli, you have the killer structure moduli. And in physics, this is also very important. In physics, you can think of the modular space as the parameterization of the family of physical theories. In many cases, this is just some quantum field theories. So you can think of something like this. This is, for me, some kind of modular space. So mathematically speaking, you can say that, oh yes, at every point, I'm just giving you a certain choice of the value of the moduli for some geometric object. But as a physicist, I'm kind of saying that at every point, I have a QFT there. And then I can move along this modular space from one point to the other. Physically speaking, this is just doing the deformation of the QFT. If your QFT is a Lagrangian formalism theory, you can say that I have the action, and then I'm just deforming the action a little bit. And then, of course, the coupling constant, which is embedded into this variation of the Lagrangian, will tell you how your theory moves in a theory space. So that's the physical notion of the modular space. So today, when I say modular space, I will be very broadly speaking that it can be a genuine conformal manifold for a conformal field theory, or it could just be some kind of parameter space for some very simple QFT, which might not have some very nice sigma model geometric meaning from the mathematical point of view. So what about the symmetries? Like, why do I care about the symmetries from the modular space point of view? The very interesting benchmark would still be our Calabi-Yau case. So for Calabi-Yau, of course, we all know that we have, the complex moduli and the killer moduli. Physically speaking, this modular space can be exactly reproduced from two-dimensional 2, 2 at CFT with the target space, or I can just say on X. X is my Calabi-Yau. So you can think of some two-dimensional n equal to 2, 2 superconformal field theory, which is the sigma model superconformal theory for me. The sigma model means it's, you can think of it as a map from the worldsheet to some target space. Physically speaking, you can write down the Lagrangian for this two-dimensional quantum field theory with the space-time coordinate is the worldsheet coordinate, and you are just defining some bosonic and a fermionic field which is living in the target space, or describing the propagating strings in target space. So in this case, the modular space of the physical theory coincide with the geometric modular space of the Calabi-Yau. I can write down all kinds of operators in this superconformal field theory, which I will focus on the exact marginal deformation operator, which means that if I choose that operator, and then I do this deformation of my Lagrangian, okay, OI is the operator I choose, and times the coupling constant lambda I. I want, after doing this deformation, I'm still lying in the superconformal field theory family instead of make it not conformal and turn on the arc flow, then flow to some other fixed point. Okay, I want to do exactly marginal deformation. And the family of these operators, of course, will give you how to parameterize the conformal manifold for the conformal field theory from the physical point of view. And this lambda will become the coordinate or the parameterization of the conformal manifold. So in this case, it's a very well-known fact that the conformal manifold for this SCFT is the modular space of the target space Calabi-Yau. So, and then you might ask, okay, but what's so special about the Calabi-Yau? Because of course I can write down any two-dimensional n equal 2, 2 superconformal field theory, write down the complete set of the exact marginal deformations and talk about the conformal manifold of it. What is the speciality of the Calabi-Yau sigma model at SCFT? Well, in the Calabi-Yau sigma model at SCFT, you not only have these exactly marginal operators, you also, geometrically speaking, you have this very special holomorphic top form. I'm writing this for the Calabi-Yau threefold case. This special holomorphic top form is globally well-defined on any point of the modular space. So let me just call this SCFT. On every point on the modular space of the n equal to 2, 2 sigma model conformal manifold, you have this operator. So you can ask, if I'm moving or if I do the deformation on the modular space, what happens or what this operator, globally well-defined operator, can tell me. So geometrically speaking, this is just a holomorphic top form, but on the worldsheet at SCFT, it has its counterpart. You can write something like this. Okay, the I, J, K are just the space-time target space coordinates labeling. So this is the operator you can write down. This is actually, you can check, this is the chiral primary, which means it's also one of the well-defined massless state in the worldsheet string theory. And of course, use this operator, you can define a vacuum in the Neville-Schwarz sector by the spectral flow operator, which means you have space-time supersymmetry. Of course, for Calabi-Yau, we have space-time supersymmetry. You can map it, you can map the Neville-Schwarz state corresponding to this operator by the, okay, great. So let me go step by step. So in the CFT, you have state operator correspondence. This is a well-defined primary operator. So this will give you some Neville-Schwarz sector vacuum or Neville-Schwarz sector state. And then if you have space-time supersymmetry on worldsheet, it means that you have an automorphism called the spectral flow. The spectral flow will map the Neville-Schwarz sector state to the Raman sector state. And the Raman sector state, of course, the Raman sector state on the left moving sector and also on the right moving sector. So basically you can ask, if you know the basic thing about string theory, of course, if you have the closed string, you need to consider left moving sector and right moving sector. So you have NS, NS, NSR, RNS, and RR. Okay? So this RR sector will give you the cohomology or the homology class of the target space. Very physically speaking, it is because we already know that all kinds of higher gauge, like this C and this kind of differential forms in the string theory, they come from the Raman-Raman field. So intuitively speaking, you can think of the RR Raman-Raman field are telling me what cohomology class I have in the target space geometry. So the interesting thing in the Calabi-Yau case is that you can consider this operator and ask what is the state in the Navier-Schwartz sector corresponding to this operator due to this correspondence, and use the spectral flow to map it into the R sector vacuum. And then you can ask what or how is this state transforming, or what is the global structure is formed by this state fibering over this modular space. You see, I have many exact marginal operators from the SCFT point of view, but most of these operators are giving me the tangent bundle of the conformal manifold or the modular space, because they are like how you parameterize your modular space. And this is the end of the story for most of the n equal to 2, 2 superconformal field theory. For Calabi-Yau, you have an extra operator which is well defined on every point of the modular space. Then you can ask how to fiber this thing, or how to view this thing as a section of some kind of bundle when you go along the Calabi-Yau modular space. But physically speaking, we're doing something very easy to understand. So how do I define, or what kind of modular space structure of this operator, what is the global structure? What is the structure, bundle structure generalized by this operator from the physical point of view? To answer this question, let me talk about some very down-to-the-earth physics. What is known as Barry phase? So what is Barry phase? Barry phase is basically saying that if I have a quantum system with the Hamiltonian, and then I can ask, okay, of course, I can have some kind of, vacuum eigenstate, which is defined by this very easy equation. And then I can ask, okay, if my quantum system is embedded into a family of quantum system, which is labeled by some parameterization lambda, and if I do some adiabatically variation, is there anything I can say about this energy eigenstate? Because this energy eigenstate is well defined on every point of the modular space of the quantum mechanics. You can think of, I have a family of, you can think of this as the family of the quantum mechanics now. At every point, I have a Hamiltonian system, and I can ask, how do I fiber this state over the parameter space, over the theory space of the Hamiltonian system?
You mean after taking the adiabatic limit?
Yes, after taking the Bethe limit, yes. So this gives you this definition, or this notation, that you can choose a state. Usually it's just some kind of energy eigenstate, so that it's globally well defined on the parameter space. You have psi lambda, and you ask this question, or you do this computation. Okay, this lambda, you can think of this as the vector. So there are many directions in my theory space to parameterize the Hamiltonian, and I choose one of the direction to compute its partial derivative. And this is something you can compute. And you can define this as a gauge field, or a component of the connection. And then you need to also to persuade yourself that, okay, this is indeed a gauge field instead of some very weird result which I don't know how to interpret. So what you can check is if I do such transformation, this is my state. Of course, I'm free to do this kind of rotation of my state, the phase rotation of my state. And I compute again what happens to this A. You realize realize this is indeed the gauge transformation rule for a U1 field in this case. So this means, physically speaking, I'm just extracting a state and compute this inner product with respect to the partial derivative of the parameter space of my theory. But this AI indeed has an interpretation as a U1 gauge field, since it has this very nice gauge transformation rule, if you really do the U1 phase rotation of your state. And then, of course, you can do such definition. Since it's a U1 gauge field, you can define its field strength. So this thing is called the Berry phase in the quantum mechanical terminology, okay? You can think of this is defining, mathematically speaking, this is defining a line bundle over the parameter space or over the theory space of your Hamiltonian system. The state you are choosing is giving you the section of this line bundle. The whole state space fibering over the theory space is actually the fiber of this line bundle, and the connection of this line bundle is the AI field you're computing here by definition of this. And then you have the Berry curvature. So this is, physically speaking, the structure over the modular space in the sense of quantum mechanical modular space. In this case, it's not really modular space, it's just the parameter space. Okay, now we can talk about the Calabi-Yau. So Calabi-Yau works exactly the same way. I mean, this thing is like known for a long time. I'm just rephrasing it in a very phase way. So if you feel comfortable or not, just if you not feel comfortable, just ask me questions. I can try to re-explain it to you. So the spectral, this operator is playing a very special role. We already know. This is one of the this is one of the defining calibrated form of Calabi-Yau, the holomorphic top form. So you define this operator, as I said, it's a primary field, of course, and then you can find its Navier-Schwarz vacuum, and then you use the spectral flow to find the Ramon vacuum state. That's great. So this is the state I would like to think of fibering over the Calabi-Yau modular space and move along and to see what structure I have over the modular space. So the thing I can compute is this, which you can define this as e to the minus k. You will know what this k is after I say a few more words here. And then you can define such Berry phase. I'm not writing it in component. I'm just writing A as the one form, like the total one form. Okay, you can decompose D into using the chain rule to different components, but I won't really do that. So now you have this. And then you can find out that this A is actually, sorry, where is it? Yeah. And then you can find out that this is actually dk minus just the holomorphic derivative and the anti-holomorphic derivative of this k. So what is dA? What is the Berry curvature corresponding to this very special globally well-defined operator?
There's no additional factors like e to the minus k in the formula for A? Because you're...
Sorry, what the question?
If I'm calculating A, would I not get like an additional factor of e to the minus k if I'm just taking the derivative? Like naively, that looks to me like what I would get, but you don't have. Oh, there's a little. Yeah, I'm just being sloppy here. So strictly speaking, you should try to first normalize this state. Okay. And then do yeah. Okay. Thanks. Yeah. Thank you. Because in the end, yeah. Let me maybe some other. Yeah. Okay. Good. Maybe people might also have this problem. So yeah, it just in the end, after you renormalize thing, you can find out how the A is transformed, but you can absorb that back in, yeah. So actually, when you're computing this, the inner product of this Ramon vacuum, what you have is the Kähler potential. And this is, by definition, the Kähler form of the modulus space. And this exactly matches the fact that if I have the modulus space for Calabi-Yau, it's not just some even dimensional space. It's a Kähler geometry. This structure has been seen by looking at the Berry phase of this very special operator, only because you're talking about the Calabi-Yau sigma model at CFT instead of very general two-component at CFT, so that you see this Kähler structure over the modulus space. So this is basically how I rephrase what people already know like for decades about the Kähler geometry of the Calabi-Yau modulus space, but this time from the Berry phase perspective. So where does the symmetry come from? This Berry phase has, of course, has the very natural definition of the connection. This connection can be think of as the shadow of the U1R symmetry of the worldsheet. Because you can think of this as because of this operator, it's transformed very nicely under the U1R symmetry. The U1R symmetry is rotating the worldsheet fermions. So for you, this is have 3, 1 U1R symmetry for U1 left and U1 right. Then when you on the modulus space, you want to compute the holonomy, or when you have the closed loop, you want to evaluate the global structure of the modulus space. This holonomy of this field have to match how the U1R symmetry acting on the holomorphic top form, or how it acting on this operator. So you can think of this as, once I have a global symmetry of the worldsheet SCFT, and it's acting very nicely on a globally well-defined operator, then there existing a U1 gauge field over the modulus space, which is corresponding to the Berry phase I computed using that operator. This is what I mean. So now we have built a very nice thing here that what I need is a global symmetry. I'll just write symmetry here. I will need a global symmetry which is well-defined on every point of the modular space. It cannot be some extended symmetry on some rational CFT point. I have to have that global symmetry every point. And I need some operator also well-defined every point on the modular space. And then I have these two information together, then in the end, this will tell me, or this will have some, then you can trace this thing into some kind of structure over the modular space. So this is basically a symmetry perspective, or the quantum mechanical Berry phase perspective of the Kähler structure of the Calabi-Yau, which come from the holomorphic top form operator. So any questions at this point? So all these things are just redoing what people already know, but we're telling it this way because we're trying to motivate what happened in the G2 and the spin 7, which we know much less than Calabi-Yau case. Yes?
What can I say about conifold points or boundaries of the Kähler code, sort of more phase transition-like phenomenon?
Yeah, I'm not sure about those. I mean, like something I can say is that if the loop you are going on the modular space is indeed surrounding some conifoid point, then you should pick up some very non-trivial holonomy. That non-trivial holonomy, I would say, should be computable from the SCFT point of view. But other than that, I'm not.
So you see that as an interior point, right? Not a point on the boundary. Like formation of a singularity. It could be something like at the infinity or the
At infinity, yes, yes.
Yeah, that I'm not sure.
Yeah, but the conic is at finite distance.
Yes, yeah, the conical point, yes. But other than that, I'm not sure. I think here I'm just saying that consider the nice patch of the module space. Not thinking the corner or the infinity, but it's definitely a very interesting open question, which I don't have a good answer now.
Because, for example, near a flop, then that scalar class is going to be 0, which basically means
Exactly. Yeah, yes.
So are you losing information there?
I think I would think I'm not sure. I would like to say the UR symmetry and the Berry phase computing there is losing some information there, but I'm not sure. Yeah. Okay, so there's another way to see how this symmetry works, or there's another shadow of the globe symmetry of the worldsheet. Is the I think people can still see here, right? Yes. Let me don't use gauge. Is that every global symmetry is a very general yoga, that every global symmetry, I mean internal global symmetry, let's be careful, internal global symmetry on the worldsheet corresponding to some local symmetry in space-time or gauge symmetry in space-time. I'm using local because I'm just trying to be careful. Some kind of local symmetry in the space-time, they're not really introduced also with some dynamical gauge field. They're just local symmetry instead of having some propagating gauge field. So let me use local symmetry here. So in this case, of course, the U1R, we have said that, oh yes, together with this operator, it gives me the Kähler structure over the modular space. What happened in the space-time, because you can think of this is a local U1 gauge field over the modular space. You can think of this has a space-time counterpart, which is just the U1 background field of the local U1 symmetry in space-time. How is this thing look like? I'll just do very schematic writing here. So in space-time, if you have type, oh yes, all the talk will be in type 2, sorry, because I'm always talk about non-chiral supersymmetry of the worldsheet, so it's all type 2. So in type 2, what you really have, of course, is falling to supergravity on Calabi-Yau threefold. It can be type 2 or type 2b. It's no matter what, you can use mirror symmetry to swapping the complex structure and the Kähler structure. I don't care. In this case, you have SU2 R times U1R. The space-time local U1 is actually inside of this R symmetry. In supergravity, the R, I mean, if you are a KFT person, you might get used to seeing that the R symmetry is some internal global symmetry for you, but in supergravity, this R symmetry is a local symmetry. If you are not talking about gauged supergravity, it is a local symmetry without dynamical gauge field. If you are talking about gauged supergravity, you are gauging the R symmetry, then you are introducing me the dynamical gauge field. Here I'm talking about ungauged version, so it's just a local gauge symmetry for me. So it's just a local R symmetry for me. The U1 here has a background field, which I'm using R to denote it, can be written as, using the chain rule. Again, after the compactification, I will have some kind of many scalars which will parameterize the modular space of the internal Calabi-Yau. It will have the same Kähler potential here, but this time the Kähler potential is for the scalars in space-time theory instead of for the coupling constant of the worldsheet SCFT. So I'm using phi here. You can think of this K as phi at phi bar, very schematically. And minus the complex conjugate of this.
So this is a non-dynamical gauge field?
Yes, this is a background gauge field. It's not, so I don't introduce kinetic term for it.
Oh, okay.
It's just the background gauge field.
Okay.
But it's a local symmetry background instead of a global symmetry background.
Yes.
Or you can think of that when you do the R symmetry transformation now, the symmetry transformation parameter or variable will dependent on space-time coordinate. Yeah. So here, yeah, let me try to be clean to people who are not familiar with it. This I is parameterize different scalars, different moduli in my space-time supergravity. This mu is the parameterization or is the component for my space-time coordinate. So I'm just doing the chain rule here. So this is the U1 gate local symmetry background field. You can think of this as the space-time counterpart of this vector space over the modular space as all come from or as the result if you're tracing how the U1R symmetry works or how the U1R symmetry acting on the globally well-defined vertex operator of the worldsheet CFT.
So questions? Can I think of that guy as the pullback of the gauge field on the moduli space along the back?
Yes. That's another quicker way to think of it. Yes, you can think of it just as the pullback. Yeah. Okay, I'm now using half of my time to set up the stage. Now let's move to something new. So the Calabi-Yau case is very nice. The modular space is complex, is scalar. You know, the 2,2 supersymmetry is very nice in 2D because you have a very nice control of the quantum correction. That's why the geometric modular space is exactly the same as the physical modular space or the physical conformal manifold of the SCFT. And the UR symmetry is not anomalous on the worldsheet. As a global symmetry, it is a real global symmetry, so it's free of chiral anomaly, and it is free of 't-Hooft anomaly. So it's like the cleanest symmetry structure you can think of as a QFT person. Now let me ask the next question. What if my worldsheet global symmetry is 't-Hooft anomalous? I don't want it to be chiral anomalous because chiral anomaly means I don't really have that symmetry at a quantum level. I don't want that. I still want a quantum theory with that symmetry. So I'm asking, what if it's 't-Hooft anomalous? What can I say about the space-time counterpart? What is the local space-time symmetry for an anomalous worldsheet global symmetry? This can be asked, has nothing to do with the interest of the modular space structure. It's a very natural question to ask as a string theorist if you are interested in symmetry. Give me a worldsheet theory with a globe symmetry, which is 't-Hooft anomalous. How does space-time theory see this anomaly? Other than just seeing that, oh yes, there is a gauge symmetry, where the anomaly information goes. And you can ask further that, okay, since I know that this space-time local symmetry is a counterpart or it's associated to the modular space structure of this line bundle as a connection, what can I say something about that? So since in my title on the website, I said baby steps, so I cannot answer your question about what is the exact structure over the modular space today. But I will shed some light from this perspective. Let's consider the bosonic string theory. Compactify on a compact S1. So in this case, in the previous case, I'm saying that, oh, I have a Calabi-Yau. So of course, I have the eternal geometry CFT sector is the 2,2 sigma model. So here it's very easy. It's just the sigma 1 compact boson. So in this case, you have a very naive modular space. Usually people, strictly speaking, you should not call it modular space, but let me just say you have the radius R of this S1 as the parameter space of your sigma 1 compact boson theory. I'm not talking about the abstract sigma 1 CFT with the orbifold branch, okay? I'm just thinking of just a circle as my internal CFT. I'm just using the radius of the circle as the parameter. So in this theory, as we all learn Paczynski, you have U1 momentum symmetry, which is telling you the position modular on the circle. You also have U1 winding symmetry, which is telling you how the string can wrapping on the S1, how many times. And you have a charge conjugation. Let me use C to C, which is just a flipped coordinate sign parameterizing the S1. Okay, so if you have X as the bosonic field, parameterizing the S1 as the space-time boson, as the worldsheet boson, you can check that the sigma-1 compact boson CFT has this symmetry. This is the G2 charge conjugation. The interesting thing about this global symmetry of the sigma-1 compact boson is that there is a mixed tooth anomaly between the U1 winding symmetry and the U1 momentum symmetry. There's a mixed anomaly here. So we can ask now, what is the space-time interpretation of this thing? So in the space-time, of course, you have the 25-dimensional effective theory. What you really have is you have a one field, which is associated to the U1 momentum symmetry. That's the gauge field for the space-time gauge symmetry, come from the U1 momentum. And you have B1 is the dynamical gauge field. It's not background now. Okay, it's the dynamical gauge field for the winding symmetry. And you have 25-dimensional B2 field. Okay, it's just come from the 26-dimensional reduction of the B2 field of the bosonic string. The interesting thing is that if you see the gauge transmission rule of all these fields, you see that the A1, which is the momentum symmetry field, has the very conventional gauge transmission rule. But the B2 field, this time, is transformed in this way. It is transformed in addition to the, oh yes, I should also have the conventional gauge transmission part. But together with the B1 field and the gauge parameter, the gauge transmission parameter of the A1 field. So the physically well-defined flux in this case is dB2. When I say physically, I mean when you talk about the flux, you need it to be gauge invariant. When you do gauge transmission, you don't want the flux to change, or you don't want the field strength to change, right? So physically, this is what you have. Where H2, locally speaking, is just the dB1. Of course, there are cases that in non-trivial topology, B1 and A1 connection might not globally well-defined, but that's why I'm using H2 here. But locally speaking, you can think of this is always holding for you. So the punchline of the space-time structure now is this. The punchline is that, yes, I have U1 square global symmetry on the worldsheet. In the space-time, I still have the background, I still have the gauge field at gauge symmetry background for both momentum and winding, but they don't really exist solely as a U1 square gauge symmetry in the space-time. They are mixing with the derb in the space-time. They're mixing with the B2 field in the 25-dimensional effective theory. This equation of motion, mathematically speaking, is telling you the worldsheet anomaly becomes I don't think people can see here. Let me write there. The worldsheet global symmetry anomaly is now packaged into the continuous two group. So this is how you distinguish with the same global symmetry but different anomalies on worldsheet from the space-time theory point of view. If you have the Tooth anomalies, at least in this case for the U1 square, in the end you will find that this anomaly somehow got resolved by extending to a two group. Yes?
And would you say that the class of the gerb, the class of the B2 defines the central extension? Is that what's happening?
Yes.
I see. So it's a two group specified by B field.
Yes, specified by B field. You can think of the you can think of this as the gauged two group. With this point is the U1 with the zero form symmetry here, one form symmetry here. The one form symmetry background is the gerb. The zero form symmetry background is just the two gauge field come from the gauge boson corresponding to the global symmetry here. And then these things together give you the two group because of this modified Bianchi identity. And then we can ask the question about what is the modular space structure of this, because the modular space is very easy. It's a line. Okay, you're from the radius 1 to radius infinity. I'm not drawing 0 to 1 because there's a T-duality. So I think I would like to propose, which we don't have any real answer of that. Since we have the two group in the space-time, we would like to say that we're having some kind of anomalous structure of the U. Like you fiber the U1 square, you can think of you have some kind of line bundle or like two line bundles associated with the U1 square. You fiber it over the modular space, but there are some kind of anomaly information here, which makes this as more like a stack instead of a bundle. This can be more concrete if I'm considering the Z2 of this U1. In this finite subgroup case, the Z2 diagonal symmetry of the U1 square, it is self-anomalous. So the best way to describe it as the global symmetry on the worldsheet is the fusion category vec Z2 with the twist omega. So, of course, it is still an open question, but the baby step of this computation in space-time motivate us to propose that maybe you should think of some stack over the modular space whose fiber is the fusion category instead of just the Z2. If you just think of Z2 global symmetry, then it's just a real line bundle over the modular space. It's kind of trivial, but if you have this, we would like to propose that there should be a fiber of the fusion category. Sorry, the fiber of the fusion category over the modular space, which give you some kind of stack. Yes?
Wouldn't you just say, like, why would you not want to just say that, like, the two group is fibered over the moduli space?
I'm a little bit struggled because this is a one-dimensional space. I'm not sure how to support a B2 field on the one-dimensional space. Like I need two.
It's like abelian gerb over the one-dimensional space, right? Like it comes with a map to like the classifying for the two group. Like I don't know.
I think I'm struggled by some physical meaning of having a two-form field over a one-dimensional space.
I see what you mean.
But one of my collaborator, Eric, came to say that the two group fibered over this thing is the same as you fiber this fusion category, which I don't quite understand why.
I think.
But physically speaking, I'm not really comfortable with fibering two group instead of just fibering the fusion category as the stack.
Maybe we can discuss later, but I think I understand the two group better because at least you can represent that by a map to the classifying space.
Yes.
Like
that part I agree. I'm just physically speaking have a very hard time because everything comes from the Calabi-Yau. In Calabi-Yau, I have of course higher even dimensional modular space. Of course, I can very easily support a U1 field. Over that.
Yeah.
Yes. Do you think this might be an artifact of your example in which you have one geometric moduli?
Yes, I think it will be easier if I have the ring modular space instead. Yes, yes. I think it might be easier, but even before, even I resolve that example, I still need to come back this and to pursue to make myself confident or convince myself why I can support two group over one-dimensional space, over one-dimensional base space. I'm just physically speaking not comfortable with that. If you are saying that the structure for the classifying space and then this is the thing fibering over this, I'm totally fine with it. I'm just not sure what is the two-group Berry phase version of this thing. Yeah.
I guess it's a bit. I guess in this example, it's topologically trivial anyway, right? So you.
Yeah, like you don't really have
No
non-trivial global structure over a line.
Yeah.
Yeah, right.
So at the self-dual point, you have U2 gauge symmetry enhancement, right?
Ah.
That means you have a map from G hat to U2. So is this map easy to say?
I think I would like to use the common. I think I would like to use the global symmetry, which is common on every point of the modular space.
Yes.
Because I would like to talk about the global structure over the modular space. Of course, on every rational point, you will have monstrous extended global symmetry, which is very large. But if you deform the theory a little bit, you lose all those symmetries. So I don't really care what the structure of those things.
There should be a map, right? There should be a map from the generic gauge group to some enhanced gauge group.
Like a sub-exact sequence defined as sub-extension.
Yes.
Oh, you mean in this? You mean at least in the space time, I should be able to talk about what is the two group extension at the self-dual point, right?
Yes.
I think that might be the case. Yes, here it will become some kind of SU2 or SU2 times SU2. I think it's SU2 times SU2 multi 2.
Right?
So yeah, so basically the global symmetry at this point is SO4. It's SO4 because it's SU2 squared mod Z2. So I would say this should be a SO4 here, but I have no idea how to classify that two group. I mean, for this case, I know it's labeled by Z cube, but for that case, I'm not sure what's happening. Yes, and also you will lose that structure if you move a little bit from that point.
Yes. So if you're describing the two group as cross module, then it's still clear what to do at the self-dual point, right? Because you have like you have the SU2 squared over Z2, right? And then you have like the U1 action on SU2 squared by the automorphisms, right? So
yeah, that part should be fine. But yeah, if it's SU2, it's fine. But the real global symmetry is at SO4. I'm not that comfortable with how that works.
Oh, I see.
Like without this quotient, I think I'm good how it works. Yeah. Other question? Okay. Now let's move to the next case. So as a QFT or CFT person, you can ask the following question. What is the worldsheet theory has non-invertible global symmetry? In this case, we're doing an even worse job. We don't know what is the space-time interpretation is, and we don't know what the structure is. Yes?
Sorry, can I just go back and ask one more question? So for the anomalous case, are you saying that whenever I have a mixed anomaly, it will be a two-group structure, or is the two-group particular to this example?
I would say the anomaly on the worldsheet will always become some higher structure in space-time, but I'm not sure whether it will always be the two group or not. I think it will always be a higher structure. I think it will, yeah, right. Maybe even not higher group-like, but it will become some higher structure because you don't want to lose the information of the anomaly. But you cannot really bring that anomaly with you in space-time because it's a gauge symmetry.
Exactly.
So philosophically speaking, I would say it's always some higher structure. Yes. As a QFT person, you can ask, okay, what is the case for the non-invertible? Or as a string theorist, you can ask, oh, what happens if I go from Calabi-Yau to G2 and spin 7? In the end, you find that these two interests coincide in this case, because we indeed can find globally well-defined non-invertible symmetry for the G2 and spin 7 theory. Let me explain it a little bit. Siri is talking to me. I'm not sure why. I can have on G2 or on spin 7. In this case, the best I can do so far is to tell you what is the globally well-defined non-invertible symmetry for G2 and spin 7. And I can tell you how the closed string state and how the de Bruijn boundary state are transformed under that. And I conjecture there should be some higher category structure for this thing in space-time. And over the modular space, I'm thinking something very similar to the VAC-Z2 omega case. Like I'm also fibering the fusion category, describing the non-invertible symmetry for these two cases over the modular space. But those things are just conjecture. The baby step we have taken is find the well-defined non-invertible symmetry, discussing how it acting on the closed string state and the de Bruijn bound state, okay? So it would be a next step to do it in the future. So in this case, you have n equal to 1, 1 at CFT. So you ask the same question as the 2, 2 and the Calabi-Yau case. Compared to the conventional, compared to the most general n equal to 1 at CFT, what are the difference of these things? They are different, of course, because they are also special holonomic manifold. So they have calibrated differential form, which is one of the defining data of these things. For G2, you have associative 3 form. Of course, by definition, you also have the co-associated 4 form as the Hodge dual of this thing. And yeah, let me write things here. This whole thing is a 4 form. And then for the spin 7, you have self-dual 4 form, which is known as the KD4 form, okay? Those are the calibrated forms. So this will play exactly the same role as the holomorphic top form, which is one of the defining data of the Calabi-Yau structure. But the interesting thing is that if you only look at the field space, if you only look at the field theory structure of the n equal to 1, at CFT, it's a real supersymmetry. There's no U1 charge. I mean, if you want a U1, you need complex to do the phase rotations. The best you can do is that, okay, I have minus 1 to the f. I can define this as the Z2R symmetry. It's just flipping the sign of the real fermions on the left moving sector and the right moving sector. Let me do it a little bit, L and R here. But I will show that there are extensions of this Z2R symmetry into non-invertible. What I'm going to do, I will write, let's focus on the spin 7 case. The G2 case works exactly the same way. I will do exactly the same thing as the Calabi-Yau case by building you the vertex operator on worldsheet with respect in terms of the worldsheet fermions. And I'm asked what property of this thing. I define this operator as I. The interesting thing is, if you compute the OPE, operator product expansion in the CFT point of view, if you are a mathematician, that's what OPE means. If you compute the OPE, you find the structure is exactly the same up to normalization. It's exactly the same as the stress tensor of any bosonic CFT. So what I'm going to do, this is actually what I'm doing. This is what Krummer and Schatzberry doing in their very profound paper. You can use this operator to extend the n equal to 1 superconformal algebra, because they also have a very nice structure of the OPE, and you can compute other operators OPE with these operators. You find a closed algebra. So this is an extended version of the equal to 1 superconformal algebra. What you do is you can define the stress tensor, a new stress tensor, by normalize this operator a little bit. And then this thing is the generator, or give you the generator of the C equal to 1/2 Virasoro algebra. So there is Ising-Cairo algebra hidden inside the extended n equal to 1 superconformal algebra. Let me recap a little bit what I'm saying. Very nice. For G2, this is spin 7. For G2, this is tricritical Ising. Let me recap what I'm saying. So your starting point is, I'm a 2D CFT person. I can't think of any n equal to 1, 1 at CFT as I like. But now I'm saying that, no, there is a special class of 1, 1 at CFT, which is sigma model at CFT, with geometric target space spin 7 or G2. And then the calibrated form, which is defining the structure of this exceptional holonomic manifold, will give you extra globally well-defined vertex operator. This vertex operator have its own OPE, of course has OPEs with all other strengths, with the Euro stress tensor and the superpartner in the equal to 1 superconformal algebra. You find out that they form a closed algebra. So this is a larger n equal to 1 superconformal algebra, or extended n equal to 1 superconformal algebra. And there is a hidden subsector in this superconformal algebra, which is the RCFT sector, or is the Ising category sector, or is the tricritical Ising category sector. Another way to see this is, let's still go this way. So in the Calabi-Yau case, why we have a U1R symmetry? Why there's a U1 floating around? Because for general 2,2 theory, it always has a Kähler structure, it's UN, but Calabi-Yau is SUN. So in the end, you are left over with a U1 to play around as the global symmetry on the worldsheet. In the spin 7 case, you can have SO8, because this is the most general structure group for 8-dimensional real manifold. You're asking the very special thing about what this quotient means. This result is not a group. It's not as nice as this, but it's a nice structure as the current algebra. You can consider WW model very abstractly and do this quotient. You can compute its central charge. It is exactly C equal to 1/2. Yes? It's because I'm just taking the worldsheet fermion. I count how many worldsheet fermions and then I do the Bose-ization. After the Bose-ization, it will become the level 1 WW model. That's right. Yeah, thank you for the clarification.
I think you said it, but so you care only about G structure rather than G velocity.
Yes, yeah, right. And then, yeah, I need to, can I have like 5 more minutes?
Sure, go ahead.
Yeah. So very nice. So where's the globe symmetry? Where's the globe symmetry? Of course, you're telling me that, yes, this is just a local chiral algebra which is embedded into this SCFT with the very nice target space. Then what is the symmetry? The key step here is to decompose the n equal to 1 stress tensor into the Ising part and the rest. The RA just means the rest. And you'll find out that they're commuting. Here I'm just writing in the OPE way. When I say they're commuting, I mean if you expand those into modes as the algebra generators, you will find that the bracket is, yeah, the bracket is 0. So they're commuting. This is very nice because how we write closed string state. We ask what is the primary fields as from the CFT point of view, right? And then we write down the state corresponding to the primary operators as the state operator correspondence. Now I'm saying that, oh, weight. Now, if you want to write massless state, which is the highest weight state from the conformal field theory point of view, you can decompose any conformal dimension labeling this state into the eigenconformal dimension and the rest of it. So all the closed string state corresponding to the cohomology class H1, H2, H3 of this geometry can be written with the first factor as the primary field of the minimum model chiral algebra. For Ising, this will be just 0, 1/2, 1/16. And this thing will be determined by preserving the supersymmetry of the spacetime, because you want the total dimension to satisfy certain conditions in the R sector and the Navier-Schwartz sector, right? Okay, again, where is the symmetry? The symmetry is saying that, okay, for a rational CFT, I can write down primary fields, and there are always a set of Valendian lines, which is one-to-one correspondence to the primary fields, which is commuting with the stress tensor. I mean, they're even commuting with the full chiral algebra, but they're commuting with the stress tensor. If they're commuting with the stress tensor, by definition, they're topological. So in this case, I can always write. Now I'm decomposing my full Virasoro algebra into the Ising chiral algebra and the rest of it. Then I can write the Valendian line operator for the chiral algebra sector, for the minimum model chiral algebra sector, times with the trivial line operator, which is always commuting with this set of operator. This only happens because this very nice structure. You can't really generally decompose your stress and say that's the case. Okay, this is only because the Virasoro generator has that very nice structure. So this means that on the spin 7, I would have a Ising categorical symmetry. And for the G2, I have tricular Ising categorical symmetries. For the Ising category symmetries, I mean you have a Z2 symmetry. This Z2, I don't have time to show it explicitly. This Z2 is the Z2R symmetry. You're embedding the Z2R symmetry into a larger non-invertible symmetry. And it also, of course, has this non-invertible topological defect, which is the Kramer-Weiner line. From the kinetic matter point of view, if you are a categorical person, you would call this tempora Yamagami over a Z2. For the tricular Ising, you also have this symmetry. In addition to the Fibonacci category. Of course, from the kinetic matter or CFT point of view, some people call this Li-Yang model category, but it is the same. And then you can write down every kind of closed string state based on the conformal weight of the chiral algebra. And we already know how this transform under that, because we know the Morse-Seiberg data of how the Valendian line acting on the chiral primaries of the minimum model. I just need to look at how these lines, as Valendian lines of the minimum model, acting on the first sector, because it won't acting anything on the second sector. So I know how the closed string state is acting on it. And then let me quickly. And then I also know how the D-brane is acted by. Because for any CFT, if you have conformal boundaries, conformal boundary conditions, if the CFT has non-invertible global symmetry captured by a field in category C, the conformal boundary always arranged into a module category over C. Physically speaking, module category just telling you the repetition theory of the Fusion category. So now, no matter what boundary conditions you write for me, or no matter what boundary conditions you write for me, they're D-branes wrapping submanifold inside spin 7 or G2. I can always arrange it a charge or a repetition to that D-brane so that it is the module category of the Fusion category. In this case, the Ising category and the tricular Ising category, they only have one module category, which is itself. It's the regular module category. So basically, all the D branes can be arranged into class as these things. How the symmetry acting on that? By the fusion rule. If I have a topological line, it can acting on the D brane, which is labeled by eta, then it will become this class of D branes. And you can do the same thing. You can have an n times n, which this will become this will become the sum over two classes of D branes. And then, since it's non-invertible, so I don't have the answer about what space-time happening, but I would conjecture that there should be some higher categorical structure so that I can pull this non-invertible symmetry at some kind of local background into space-time, but it is extended by some gerb or by some other things in the space-time. I don't know it yet explicitly. And I do the same conjecture as the modular space. Now the modular space for the spin 7, it's B2 plus B4 minus plus 1. This is come from the H0. This come from the anti-self-dual 4 form in the spin 7. This is come from the flat B2 field deformation of the worldsheet theory. So this is the physical modular space. This is the geometric modular space. Because we have real supersymmetry, the geometric modular space is not the same as the physical modular space. But I conjecture that I should take the self-dual 4 form, which is the defining Katie 4 form, to fibering over this modular space. And the structure I should think of associated with the symmetry, it's some kind of Ising category fibering over the modular space, which is governing how this self-dual 4 form is transformed or is glued along the modular space. So it's some kind of stack, but mathematically I'm not sure how to really well define it yet. So yeah, so this is basically all the thing I would like to say today as the baby steps beyond the modular space case over the modular, beyond the Calabi-Yau over the modular space and also the space-time symmetry. Thank you. And sorry for going over time.
We had some questions along the way. Any more questions? So is this symmetry broken? Okay.
This symmetry is a well-defined. This symmetry is a genuine globe symmetry on the worldsheet at CFT.
Yeah, but as space-time.
In space-time, I would say they are gauged, but not by themselves. They are mixing with some other thing to build a higher category structure. But it's just a conjecture. I don't have the computation as clean as the sigma-1 compact boson case.
Yeah, so basically you are saying that this symmetry should act on other branes and
they indeed act on branes. That's why I'm saying in space-time maybe they're not broken or they are doing something because, okay, let's consider the Calabi-Yau case. You have the U1R symmetry, right? Yeah. On the worldsheet is the global symmetry which can act, yes. On the worldsheet, you can have the boundary state here. Of course, this boundary state is associated with some boundary conditions, tell you how the D brane wrapping on submanifold of Calabi-Yau. These D branes will carry U1R charge or U1, like U1 vector symmetry or U1 axion symmetry, depending on whether it's A brane or B brane, right? So you can take a topological line here, U1A or U1V, and asking how it's acting on this boundary. If it's A brane, it will carry this symmetry. Or it will transform non-trivially under the U1 vector symmetry. If it's a B brane, of course, you know it's a U1A symmetry. I'm doing exactly the same thing in the spin 7 case. In the spin 7 or in the G2 case, I still have the boundary state. What I'm asking is this topological line for me now is eta or n. I'm asking how this D brane is transformed under that. If you ask how it's something transforming under symmetry, you're asking what is the representation of that symmetry category. In the U1, the representation is just the charge. It's just the 1, 2, 3, 4, it's just the charge, right? In the non-invertible symmetry case, the representation is the module category, which is the fusion category itself. So in this case, I'm just labeling D branes as these 3 kind of states. And then this non-invertible symmetry as global symmetry on the worldsheet will acting non-trivially on the boundary state. In space-time, this will translate into there are some local non-invertible symmetry which is acting on the D brane wrapping on the submanifold in space-time. This is why I would like to conjecture the gauge symmetry is still the symmetry. Okay, at the string tree level. At the tree level, I would say the symmetry are still there in space-time. And the d-brane will transform under that. But these symmetries won't be well-defined in space-time just by themselves. They need to be extended. Let's say I have the Ising category here. Very schematically speaking, I would like to write something this. Of course, this is a very wrong thing to write. I would like to see there are some space-time thing, maybe come from B2 field, maybe come from some other things. Extend this Ising category so that it is well-defined as a gauge symmetry, because Ising category is an anomalous fusion categorical symmetry. It cannot be gauged in 2 dimensions. If you have type 2 on spin 7, which you end up with a 2-dimensional effective theory, you cannot say I have Ising gauge categorical symmetry, because Ising category has a very bad F symbol information, like the Ising category cannot be gauged as a local symmetry. So to still have information about Ising symmetry in space-time to the effective theory, the anomaly has to be resolved somehow. It's again similar to the C=1 compact boson case. The U1 square is anomalous. You can't say I have an anomalous gauge symmetry in space-time, because it's a contradicting thing to say. Anomalies by definition, 't Hooft anomaly by definition means you cannot gauge that symmetry. The way you gauge the U1 square in space-time is to first extend it U1 square into a 2 group in terms of the B2 field, and then you gauge the whole 2 group. Gauge the whole 2 group means I promote every single background field for 1-form symmetry and 0-form symmetry into dynamical propagating gauge field. Here I'm doing the same thing. I'm conjecture that there might be some finite version of background gauge field for Ising fusion category. I can gauge it because it is extended by some 2-form field or some other thing in space-time. And then in the end, this gauged higher structure is well-defined in space-time.
So there is a 't Hooft anomaly for this Ising category.
On the worldsheet, as a worldsheet global symmetry, it has a 't Hooft anomaly. Yes.
Okay, thank you.
Yes.
You said that the symmetry was preserved, you knew at tree level, but you're saying that maybe at loop level, at higher loop level, the selection rules for the Ising symmetry are broken?
Yes, I think at least for the Ising, if you're just computing the loop, it will be broken.
Okay, so generically it's broken.
Yes.
Like generic point in moduli space, like
Yes.
higher loop kind of contributions.
I would say this correction is good,
Yeah, loop correction. Yeah.
but I would say this correction is bad for Ising category.
Because there's a paper that predicts that like a
Yes,
higher loop level
yes.
generically gets broken to maximal.
Actually, it's very easy to see. You can just put a different line. You can put different line here, and to check if it's a loop, you cannot really complete this diagram with respecting to the fusion rule on every vertex.
Sure, but are there like special points then in the moduli space that you expect to get preserved at all loop order? Like for instance, this happens in the case of this like tensionless ADS3 times S3 times T4 case.
Yes.
Tensionless string, like there's exact non-invertible symmetry on the worldsheet.
Because the tensionless thing is that the tensionless holography is actually in this region, right? It's the worldsheet description. So of course you take into account all the alpha prime description, all alpha prime effect, but the G string is
no, but like
somehow,
but at all loops.
Yes, at all loops. So yes, right.
Non-invertible global symmetry.
But I think it's a very special case. I would say in general, I would agree with the.
Are there points on the moduli space of spin 7?
I'm not sure, because we know so little about modular space of spin 7 and G2. The only example we have so far is just the Joyce orbifold. I think that's under best control, or maybe some construction, I guess. But I have no idea about how that works.
Right.
The only thing I have control under my fingertip is just the Joyce orbifold.
Right.
But I don't see where is the special point which I can indeed convince myself preserve the non-invertible symmetry in space-time. Yes.
So I'm trying to think of this non-invertible fusion rule from the space-time perspective. So this is reminiscent of Anani Witten, and there it's crucial that you produce branes that have a dimension jump. So I was wondering if there's any sort of way you could try to see this from the perspective you presented of these lines acting on these boundary states.
Oh, the Hansen-Witten the Hansen-Witten you are thinking is, you mean if I have a brain in space-time as the non-invertible defect? Or it's something, is that your, is that?
Yeah, the picture where you
that,
slide one brain across the other and you...
Yeah. And S5, D5,
Right.
and then D5, and S5, then D3.
Exactly. So this dimension jump there.
Yeah.
And then the way, if I recall correctly, they see this by matching the moduli space of the space of open strings stretching through the brain.
Yes.
I think it's because you can see this explicitly from the Coulomb branch of the 3D effective theory.
But is there a counterpart of this space-time story in terms of the topological lines fusing to the boundary states in the manner that you described? Because it seems like this the idea that the module over the Ising category big itself just tells you that algebraically this action will just reshuffle the labels and possibly decompose into a sum of identities.
Yeah, I think it might be the case.
The whole data you can guess.
But I'm not sure what is the topological line. I'm not sure what is the counterpart in space-time
I mean, you would say
of
that
the topological line on the worldsheet.
Yeah, that's the core of the question.
Yeah. I'm a big.
I mean, the fact that you're saying that L maps a brain to another brain sounds like you're not creating some lower dimensional object.
I'm thinking something like that. But in space-time, I'm not exactly sure how this is manipulated. I mean, of course, I can check. I can compute what is the submanifold corresponding to these brains labeled by the modules. But I'm not sure in space-time what does this mean exactly.
So because the labels of the lines are the same as the labels of the brains,
Yes.
I imagine that fusing a line and a brain is the same as fusing a brain and a
Yeah,
brain, which
yeah.
is that's the connection I was trying to make.
Yeah, that could be the case, yeah.
And in fact, when you're looking for a non-invertible symmetry, you fuse the line with its dual. So in two dimensions, they're the same. But in space-time, the NS5 is the dual of the D5s.
Yes, right.
Yes. Yes, this should, it would be interesting to think more, but I don't have a clear picture in my mind now, but yeah.